Our very own star, the sun, it seems so steady, so predictable, right? But if you look a little closer, you'll find it actually has a pulse, a magnetic heartbeat that follows this really strange and irregular rhythm. Today, we're going to unravel the mystery behind the sun's 11-year cycle. Okay, let's dive right in with our first major piece of evidence. Check this out. It's called a butterfly diagram, and believe me, it is the central clue in this whole cosmic mystery. It maps where sunspots pop up on the sun over many, many years. And as you can see, it is not random at all. It's this beautiful, clear pattern of activity that drifts in a very specific way, creating these butterfly-like wings. And this pattern, it reveals a surprisingly regular pulse. It's like a solar heartbeat that scientists have been tracking for centuries, just trying to figure out what makes our star tick. So the most obvious rhythm is this one. The number of sunspots you can see on the sun's surface rises and falls in a remarkably consistent cycle. On average, it takes about 11 years to go from one peak of activity, what we call a solar maximum, to the next. But here's the kicker, that 11-year sunspot cycle, it's only half the story. The sun's entire global magnetic field actually flips its polarity. Yup, north becomes south and south becomes north. So for the whole system to get back to where it started, it takes a full 22 years. So to even begin to understand the engine driving all of this, scientists first had to figure out the rules of the game. And they did that by just observing a few key patterns that happen every single cycle. These patterns became known as the solar laws. Okay, so clue number one is Spörer's law. At the start of a cycle, sunspots begin popping up at the mid-latitudes, around 30 to 40 degrees. But as the cycle moves along, new spots show up systematically, closer and closer to the equator. And that is what creates that distinct butterfly pattern we just saw. Next up, we have Hale's law, which tells us that sunspots are intensely magnetic. They almost always show up in pairs, with opposite magnetic polarities, kind of like the north and south poles of a bar magnet. And get this, there's an incredibly strict order to them. In the northern hemisphere, all the leading spots might be north poles, while in the southern hemisphere, they're all south poles. And then, in the next 11-year cycle, the whole thing flips. And the third clue is Joy's law. Now, this one's a bit more subtle, but it is a crucial piece of the puzzle. These magnetic pairs aren't lined up perfectly straight, they're actually slightly tilted, with the leading spot always being just a little bit closer to the equator. So, here's the bottom line. Any theory that even tries to explain what the sun is doing has to account for all of these clues. The 11-year timing, the migration towards the equator, those strict magnetic rules, and even that tiny little tilt. Okay, with all the clues laid out, it's time to meet our prime suspect, a process happening deep inside the sun that we call the solar dynamo. So what even is a dynamo? Well, at its heart, it's just any process that converts the energy of motion into a magnetic field. Think about the little dynamo on a bicycle that powers a light just by spinning. On the sun, the motion comes from its churning, rotating, super hot gas, which we call plasma. And this whole process has two key steps. The leading theory is something called the alpha-omega dynamo. First up is the omega effect. Because the sun rotates faster at its equator than at its poles, it stretches the magnetic field lines and wraps them around itself, which creates these powerful east-west magnetic bands. Then you get the alpha effect. The churning motion of hot gas, convection, twists these bands into loops. These loops then pop up at the surface as those tilted sunspot pairs we talked about, and that in turn creates a new north-south field, basically restarting the whole cycle. But just knowing the main suspect isn't enough. Our cosmic detectives still need to know how the crime was committed. Specifically, how does this dynamo make those sunspot bands, those butterfly wings, march toward the equator? And this is where the science gets really fascinating. We actually have two competing theories for what drives that beautiful march of sunspots toward the equator. So the first idea is the dynamo wave theory. It suggests that changes in the sun's rotation speed deep down create a sort of magnetic wave that just naturally travels toward the equator. The second idea is the flux-transport theory. This one's a little simpler. It proposes there's a giant slow-moving conveyor belt of plasma inside the sun that literally just carries the magnetic fields along for the ride, eventually bringing them to the surface as sunspots. And this right here is the challenge for scientists today. They are using massive supercomputers to build these incredible 3D simulations of the entire sun, trying to figure out which of these ideas, the wave, the conveyor belt, or maybe some combination of both, is what's really happening inside our star. But despite all of this incredible progress, the case of the Solar Dynamo is far from closed. In fact, some of its deepest and most fundamental secrets are still totally locked away. I mean, for starters, we still don't really have a theory for why the cycle is 11 years long. Why not 5 years or 50? The timing is probably tied to the speed of those deep plasma flows, and if we could solve this, it would be a huge leap forward in our ability to predict space weather and how it affects us here on Earth. Here's another big one. Why are sunspots confined to that butterfly region below 40 degrees latitude? Why don't we ever see them pop up near the poles? The theories hint that it might just be harder for the magnetic fields to break through the surface up there, but it is still very much an open question. And ultimately, our understanding is limited because we are pretty much blind to the deep interior of the sun. That's where the real engine is hidden, and figuring out what those giant flows are really doing is one of the biggest challenges in all of astrophysics today. And that's really the crucial takeaway, isn't it? The sun's simple 11-year rhythm that we see on the surface is the result of incredibly complex, chaotic physics happening deep inside that we are still working hard to unravel. It's just a beautiful reminder that even our closest star is still a vast frontier of discovery, with mysteries just waiting for us to solve them.